In this video, we're going to do a quick review of our angular kinematics and move into how we apply that into rotational motion and rolling motion. So we know in a rotational sense, we have a displacement in rotation, and we call that our delta theta. So our change in our rotational position or our displacement is going to be our delta theta. We can find that by a final theta minus an initial theta. And if we look at the rate at which that changes, that gives us an average angular velocity if we look at the change in the theta over the change in time. This is very similar to the kinematics equations that we've had in linear sense. We're just translating into these Greek variables which represent our angular quantities. Now the SI unit for angular velocity is radian per second. Key here, radian is actually dimensionless, and it's kind of just a placeholder there. So it's important that any angles we have are measured in radians, so that way it can be truly dimensionless, whereas degrees is a dimension, radians is kind of screwy in that it's almost like a placeholder for us. So angular velocity is measured in radians per second. And so if we look at this situation, a person spinning around and goes through two revolutions in 1.9 seconds, what's the average angular velocity? Well, that 2 revolutions needs to be converted into 12.6 radians, so we say that the average angular velocity here is 6.63 radians per second. Now, why is this negative? We're going to talk about that in a moment, but just real quick here, this is a clockwise motion, and so typically we say clockwise motion is negative, where counterclockwise motion is positive. So think about opening an angle off of the positive x-axis. When you open it counterclockwise, that is the positive direction. So that's our positive rotation. So if we want an instantaneous angular velocity, we do need to use some calculus, so we're not going to use that a ton. But there is such a thing as instantaneous angular velocity. At a particular moment, how quickly are we rotating? Typically, we're going to deal with averages. So just like there's a rate of change of our position, there's a rate of change of our velocity, and we call that our acceleration. So we have an angular acceleration. We use alpha to denote the angular acceleration, and that is equal to the change in the angular velocity over the time. Units for that are radians per second squared. So an example here, we have a jet engine that starts from it starts at a speed of negative 110 radians per second. As the plane takes off, the angular velocity of the blade reach a negative 330 radians per second in 14 seconds. We want to find the acceleration. This is just a day one kinematics problem, just using our angular quantities instead of our linear quantities. So we find the delta omega over delta t, and we get 16 radians per second squared. Now once again, this is negative just because we're showing it's a counterclockwise rotation. So if we think back to all of our kinematic equations in the linear sense, here's the list of our kinematic equations. At least some of them. There's a couple, the basic of, the average velocity is equal to v plus v naught over 2, and the average velocity is equal to delta x over t. All right, all of these, those two are kind of hidden in this one right here. All of these were in the linear sense. We're going to use all of these in the rotational sense, and they're going to be translated into these kinematic equations, where the v is replaced with omega, theta is replacing the x, and alpha is replacing the a. Notice t is the same. Time translates both linearly and rotationally, and so we can use all of these angular quantities in these angular kinematic equations. These two tables from the book help summarize what I just said and shows the translation from the linear to rotational. So anytime we're dealing with rotational kinematic problems, you're going to have the same approach that you had with regular kinematic problems. Now it's just angular rotation instead of linear movement, but it's going to be the same stuff. So if we have this problem here, the blades are whirling in a blender, and we notice that, okay, this is the axis of rotation, and we see that we have a counterclockwise rotation. So that counterclockwise rotation tells us that it's positive. So we have a positive 375 radians per second, and positive 44 radians of displacement, and we have an angular acceleration of 1740 radians per second squared. We want to find the final angular velocity of the blade. So here's our initial. This is omega naught. This is delta theta. And this is alpha. So we just have to figure out, here's 3. We need an equation that relates 4, including the one that we're trying to find, which is our final omega. So which equation relates those 4? That's the equation that is omega squared equals omega naught squared plus 2 alpha theta. Plug all the information in and solve for our unknown to get 542 radians per second. Now, when we have this rotational motion, we have what's called tangential variables as well. So such as our tangential velocity, how fast something is moving linearly on the edge of a circle, or really at any point in the rotation. And so we denote that by using v subscript t for the tangential speed. So little derivation here. That arc length that we travel through in the circle we know as s, and the angle through which we rotate, that s, r, and theta are related by theta is equal to s over r. All right, well, s divided by t is going to give us our tangential velocity, because that's our displacement divided by our time. Well, what is s from this equation? S is equal to r theta. If we plug in r theta in s's place, we notice that we have this theta over t part. Well, what's theta over t? Theta over t is omega, and so we're left with the result that our tangential velocity is r times omega. And this result shows up again in acceleration, in that our tangential acceleration is r times alpha. And so we can use this stuff. This stuff will be very helpful. And notice we don't have it written, but we had it written before, and that S, our arc length, is equal to r times theta. And so notice the common factor here. To get our linear quantity, we just take the angular quantity and multiply by the radius. So if we have a helicopter blade that has an angular speed of 6.5 revolutions per second and an angular acceleration of 1.3 revolutions per second squared, there's point 1, which is 3 meters away from the center, and point 2, which is 6.7 meters away from the center. And we want to find the magnitude of the tangential speed and the tangential acceleration. Well, this is as simple as just plugging in the stuff here of, okay, 6.5 revolutions per second. We got to multiply by 2 pi radians per revolution to get, that's 40.8 rads per second. All right, and then our tangential velocity is just multiplying by the radius, so we get 122 meters per second. Do the same thing for the acceleration. We have to do a little conversion into radians per second squared, but then multiply by the radius, and we get 24.5 meters per second squared. So that's telling us the linear acceleration at that point. One thing to note here for both of these, we have the tangential velocity moving tangent to the circle, but because we're speeding up the rate at which we're rotating, we also have an acceleration in that same direction because we're going faster, and that's tangent to the curve. Now we know that when we're in circular motion, we also have acceleration towards the center, and we call that centripetal acceleration. And we know centripetal acceleration is the tangential velocity squared over the radius. Well, if the tangential velocity is r omega, we square that, we get the result that our centripetal acceleration is r omega squared. And so this will be very useful for us in when we have the rate at which something's rotating, we square it, multiply by the radius, that gives us the centripetal acceleration. So we have a discus thrower that has a final angular speed of 15 rads per second and does this at a time of 0.27 seconds before releasing it. And so during the acceleration, the discus moves in a circular arc of radius 0.81 meters. We want to find the magnitude of the total acceleration. So there's two different types of acceleration. We have centripetal acceleration moving in towards the center, and then we have tangential acceleration because we're speeding up the rate at which we're rotating. So the vector sum of these two will give us the total acceleration, because these two have to be at 90-degree angles. One is radial, one is tangential. By definition, in our geometry, we know those are perpendicular. So we can find the centripetal acceleration using r omega squared to be 182 meters per second squared. Find the tangential acceleration from r alpha, and that gives us 45 meters per second squared. Pythag the result, and we're left with 87 meters per second squared. So when we have objects that are moving linearly, sometimes that motion is a result of rotation. Best example of that would be our car. Our car uses wheels. Those wheels rotate. That rotational motion translates into a linear motion. And so anytime we have this motion of rotation of these wheels, we see that the length that we trace out in one revolution of the wheels is going to equal the circumference, which is equal to 2 pi r, if we do a full rotation. Okay, what's pictured here is actually just one diameter, in that we're only tracing out one diameter on the road here. But we know, just logically thinking through this, if we go a full rotation, that's tracing out one full circumference of the tire, and we move linearly our circumference. And so we can look at, well, the speed, the linear speed or the linear velocity of the entire car. So the velocity that this car is moving to the right with, that can be found by looking at the radius of the wheel times the rate at which the wheel is rotating. And so, in fact, when your car has a speedometer, it uses this relationship here to calculate how fast you're going, and that's what gives you the reading on the speedometer. It actually calculates the rotation of the wheel. Knowing the radius of the wheel and given its rotation, it will then calculate your speed. So oddly enough, if you change the diameter of your wheel, that's going to screw up your speedometer. So if you get tires that are too big, than what it's using, that's going to mess up your speedometer, and it could cause some issues. And so the acceleration can be found the same way. The linear acceleration of the car will be found by the acceleration of the tires, so how fast they're increasing their rotation, and multiply that by the radius. Looking at an example here, we have a car that's starting from rest, accelerates for 20 seconds with a constant linear acceleration. So that's A, and this is T here. So we're given A and T. The radius of the tires is 33 centimeters. We want to know what is the angle through which each wheel has rotated. So we have to use some kinematics here. So we need to first convert this into alpha, so then we can find theta, because that's what we're looking for. We want to know what is theta. So wanting to know what is theta, not knowing our final velocity, we need to come up with the right kinematic equation. And the right kinematic equation is theta equals omega naught t plus 1/2 alpha t squared. We're given everything that we need. We know that this goes off to 0, and we get that this moves through a negative 484 radians. Now, why are we saying this is negative? Well, if we're saying that to the right is positive, this is accelerating to the right because it has a positive linear acceleration. And so with something moving to the right, the wheels have to rotate in the clockwise direction. So if it's rotating in the clockwise direction, that is a negative notation. We get this positive and negative notation, and a rule that comes into play here is called the right-hand rule. And this might seem confusing at first, but it is very important to be able to do what we're going to do next here with rotation. So the right-hand rule is where we use our right hand, and it is very important you use your right hand, not your left, because the left will screw everything up. So use your right hand and put your fingers in the direction of our rotation. So if we curl our fingers around the direction of rotation, so go ahead and use your hand right now and curl your fingers in the counterclockwise direction. What do you notice is happening with your thumb? Well, as you curl in the counterclockwise direction, your thumb is up, which is traditionally positive. And so we say that our omega, or our angular velocity, has a direction of up. And it's actually perpendicular, or what we call orthogonal, to the plane of rotation. Okay, so as we curl our fingers in the counterclockwise motion, our thumb is pointing up. If we change to curl our fingers around in the clockwise motion, our thumb has to turn down and is pointing down, and that we give the negative traditional direction. So we say that up is positive, and we say that down is negative, so that way this upward rotation here is the positive moving in the counterclockwise, where this downward motion here is the negative. We'll continue to practice this more, and it's going to come up again and again in other situations dealing with rotation. So it may seem a little tricky here, but I wanted to give you a brief introduction on it.